Okay, here we go with our last part, part 4 of the part A of the 2019 Physics Regents. Get to the right page. Okay, first question, big, huge picture here, so I'm going to scroll down after reading this. Diagram below represents a standing wave produced in a string by a vibrating wave generator. How many antinodes are shown in this standing wave? You need to know the difference between a node and an antinode. And I think node is a little bit more used in regular terminology. If you were to just be talking with someone, node is more likely to come up. When you think of node, you should think of a meeting place, okay? If you were looking at some sort of computer network or supply network, a node might be locations where maybe you have a lot of wires coming together, or if it's some sort of supply network, maybe it's a place where there's like a distribution center where you can send out supplies from that central place. A node is a meeting place, okay? And when we talk about standing waves on a string, a node is where in the typical picture of a standing wave, the two lines, the dashed line and the solid line, seem to meet. So that means we have nodes here, 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 and here. And obviously, with a standing wave, this picture is misleading, I think. People don't, or at least in my experience, I was misled by this picture. I did not really understand what it meant for a long time. At no point are there actually two, what are these strings? There are no strings here and here at the same time. These are just the two states that the string is moving between. At one point the string might look like this, and another point the string might look like this, okay? It's oscillating between those two because the wave generator is sending waves up the string, and it makes a standing wave pattern. Now, typically, the wave generator is moving very, 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 very fast, which means that it almost looks like there are loops to this string. But what that is your eyes and brain just not being able to process as fast as the string is moving. Now, what a node really means. Nodes are locations where there is maximum destructive interference going on. The reason that it looks like there are these loops, and at the ends of these loops are the nodes, the reason for that is because the waves that are moving up and down this string are interfering with one another. The wave generator is making waves that travel this way, and then some waves are actually bouncing off the support rod coming back down. You have two waves with approximately the same amplitude, same frequency, moving on this string in opposite directions. That means that at some points, here, 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 and here, there is maximum destructive interference going on. The wave is canceling itself out, okay? There's a part of the wave that maybe is up here. There's a part of the wave, another wave that's going back down that's maybe down here, or on these opposite sides. We add the amplitudes together and they actually cancel out. That is what these nodes are, okay? There are 4 nodes in this picture. As far as antinodes go, those are the exact opposite of nodes, okay? Those are located at this location, and this location. In other words, you can get the number of antinodes simply by counting the number of loops that you would see in one of these pictures. The answer to this is 3. The antinodes are locations where there are maximum constructive interference, okay? The fact that this rope, this string, is this far out over here, the reason it's this far out is because we have 2 smaller waves that are adding together to make this part very far from, I guess you would call it, the equilibrium position. Same thing with the dotted line here, and same thing on all of these antinodes. Antinodes are areas of maximum constructive interference, okay? So when you're asked to find antinodes, count the number of loops. Typically works. Next question is really just a definition question. What is the Doppler effect? Okay. So the Doppler effect is best described as the what? Let's go through and let's actually name all of these. Is it the bending of waves as they pass by obstacles or through openings? Keep that in mind for the next question. That is known as diffraction. That is not the same as the Doppler effect. The change in speed of a wave as the wave moves from one medium to another. No, that's not really the Doppler effect either. That is more of a refraction effect, the bending of light, which also causes it to speed up. The creation of a standing wave from 2 waves traveling in opposite directions in the same medium. No, that's interference, I guess I would say. That's what we were just talking about in the last question. A shift in the observed frequency and wavelength of a wave caused by the relative motion between the wave source and an observer. There we go. That is what we are looking for. Okay. The Doppler effect, the easiest example, you have all heard the Doppler effect and have used it and observed it since you were little kids. An ambulance coming up behind you has a very high-pitched siren going on. Once it goes past you, this pitch becomes lower. Okay, the frequency seems to change. It doesn't actually change. If you were in the ambulance, you would hear no difference whatsoever because you're moving along with the source of that sound. What happens is, as the ambulance is coming towards you, it's creating these sound waves, but these sound waves are not allowed to spread out as far as they would if the ambulance was stationary. Okay? They're kind of scrunched because the ambulance is moving, it's trying to catch up to the sound waves. So the wavelength seems to be shorter because the sound wave gets produced and it travels, but the ambulance is trying to keep up with the sound wave. That reduces the distance between wave crests. And if the wavelength decreases, the speed of the wave is just, it's a wave in air, it's not changing. If the speed is the same and the wavelength decreases, that means the frequency has to go up. The opposite happens if the ambulance is moving away from you. Okay? It's moving farther away. It's putting more distance between those wave crests because the crests are coming towards you. The ambulance is speeding off that way. The wavelength seems bigger. The speed is the same. The frequency seems lower. That is the essence of the Doppler shift. And we watched a video. We did a couple of examples to demonstrate that. So that is choice number 4. Okay, 29. And I got to make sure that you guys can see this one. So let's do. Okay, hopefully you can see. It says, which diagram represents diffraction of wavefronts as they encounter an obstacle? Remember what we just said diffraction was? Diffraction is choice number 1 in the previous question, the bending of waves as they pass by obstacles or through openings. So we need light to bend as it passes an obstacle. 3 and 4 have nothing to do with passing an obstacle. This, as you can probably hopefully tell, is reflection. And only one of these is a correct picture of reflection, number 3. So that's not diffraction. This doesn't make sense, okay? The incident ray would have to be equal to the reflected ray. We do not get that in number 4. So we're left with 1 and 2. And these are not your typical pictures of diffraction, but you should be able to figure it out. We always talk about diffraction as light passing through an opening. Maybe a better way to describe it would be light passing around a barrier. It should bend into the space beyond a barrier. And the reason it does this, I'm blanking on the guy's name right now. I cannot remember his name. But he had, it'll come to me in like 3 videos from now. But there was a rule that showed that if you have a whole bunch of point sources lined up, the light seems to keep making plane waves. If you take away those sources on the outer edges, you get the bending of light as it spreads into the areas behind the barrier. We only have, so choice number 2, the light passes the barrier but does not spread into the area around it. That is not diffraction. Choice 1 is our answer here. Okay? The light is bending into the area behind this barrier. It's going to drive me crazy that I cannot think of that guy's name. Okay, so that was choice 1. It's a diffraction question. And we're finally off of the wave questions. Now we're getting into a little bit of modern physics with question number 30. Which types of forces exist between the 2 protons in a helium nucleus? So let's talk a little bit about protons. Okay? They have mass. And they're positively charged. So, they have some mass. Any 2 objects that have mass have a gravitational force between them. And that gravitational force is always attractive. Okay? So, we have something here that says a repulsive gravitational force. That cannot be right. Okay, so we know that one cannot be right. Let's think about the positive for a second. If you have 2 positive charges, what should they do? They should repel each other. Okay? So that should be a repulsive force of gravity, or electromagnetic force. Fg is attractive. Okay, so we need a repulsive electrostatic force. 2 fits the bill. 3 and 4, they are out. They say attractive electrostatic force. So that means number 2 is the only one that should be right. But look what it says here, and an attractive strong force. This is what we talked about at the very, very end of the year. Strong force does not come up until basically the very last unit. The electrostatic force is much, much, much stronger typically with things of this size than the gravitational force. And because it's much, much, much stronger, what that means is what should happen if the strong force did not exist is those protons would just be blasted out. They would not want to be together. The gravitational force isn't strong enough to keep them together. Therefore, there must be another force keeping them together. We call that the strong nuclear force. So electrostatic force is repulsive. The strong nuclear force is attractive. That's what keeps them together inside the helium nucleus. Gravitational force is attractive, but it's way too weak to do anything.